Dear students, in last class we have completed analysis of DC electric circuits. In today's class, I will be starting next chapter, that is magnetic circuits. In this chapter, you will be studying dynamically induced EMF, statically induced EMF, series magnetic circuits, parallel magnetic circuits, and lifting power of magnets. But before we go into induced EMFs and magnetic circuits, we will have just a flashback on the definitions that you have studied in your lower standards. First definition is of magnetic line of force. In your lower standards, you have studied that if you take a bar magnet, it will be having two poles, N and S. If you place a tiny magnet near N pole, then the tiny magnet's S pole will be facing N pole. Now you can mark a point at N pole of this tiny magnet. Lift the magnet, that is this tiny magnet, and place that here. Such that S pole is directed towards the point already placed here. If you repeat this procedure of marking the point and lifting the magnet, once again placing it, then finally we'll find that you'll get set of points which will end up in S pole. Similarly, if you start from different point on the N pole, then you will get again set of points which will end up in S pole. Now if you join all these points, you will get curved lines. Starting from N pole and ending at S pole. Similarly here also. But inside the magnet we find straight lines. So now once again I will write here N pole and S pole as there is overlapping. These curved lines outside and the straight lines inside, which form a closed path, are called as magnetic lines of force. And these actually tell us that in the vicinity of this bar magnet there is a magnetic field. Such thousands of lines we can draw. We can draw such thousands of lines, and all those lines will tell us that there is magnetic field existing around this bar magnet. So now we can define what is magnetic line of force. It is an imaginary line of force that depicts magnetic field around the magnet. Now, question may arise, what is magnetic field? Magnetic field is a region where the effect of magnet may be felt. That is, if I bring small pieces of iron around this magnet, if I find that iron pieces being pulled by the magnet, it means that there is magnetic field in that region. And if the iron filings or iron pieces are not being attracted by magnet, then it means that the iron pieces are placed outside the magnetic field. Now we will write properties of magnetic lines of force. First property, outside the magnet lines of forces are directed from N to S pole. First property, outside the magnet lines of forces are directed from N to S pole and are curved. That you can see now. This is line of force and is directed from N to S pole. That means outside the magnet line of force starts from N pole and ends at S pole. Similarly on other side also. And also you can observe here the line of force outside the magnet is curved. Inside the magnet, lines of force are directed from S to N pole and are straight and parallel to each other. That also you can see now. Inside this magnet, lines of force are directed from S pole to N pole. I have shown arrow marks here, upward. And also you can observe that these lines of force are straight and parallel to each other. Now you make one more observation here. Near the poles, lines of force are very close to each other. If I draw here some more lines of force, like this, you can observe lines of force are very close to each other near two poles. But the distance between lines of force increases as they go away from the poles. That is, in this region you can see the distance between the pole. That is, in this region you can see the distance between lines of force is maximum. Same thing you can observe here also. But as they go closer to the poles, the distance between them goes on decreasing. Near the poles, the lines of force are very close to each other. And are away from each other in a plane cutting the magnet perpendicular to the axis of magnet. Fourth one, magnetic lines of force never intersect. Bunch of magnetic lines of force is called magnetic flux. It is denoted by phi. Unit of magnetic flux is Weber. Magnetic flux acting perpendicular to the perpendicular to unit area is called magnetic flux density. It is denoted by capital B. Its unit is Weber per meter square or Tesla. 1 Weber per meter square means 1 Tesla. So I can write magnetic flux density as flux by area, that is phi by A, Weber per meter square or Tesla. Next we'll write what is magnetic field. It is the region around the magnet or in the vicinity of magnet where magnetic effect can be felt. Next definition is magnetomotive force or MMF. like EMF in electric circuits that tends to circulate current. In magnetic circuits, magnetomotive force tends to set up flux. It is very similar to EMF in electric circuits. So you can write here. It is an agent that tends to set up magnetic flux in magnetic circuits when applied. MMF is calculated as number of turns in the winding into current flowing through the winding. We know that if current of I ampere flows through a coil having n number of turns, it sets up 5 Weber of flux. Now, in calculation of magnetomotive force, we have to consider current I flowing through the coil and number of turns n in the coil. Definitely unit will be ampere turns. Unit of MMF is ampere turns. Next we'll write reluctance. In electrical circuits we have resistance to oppose flow of current through the conductor. In the same way, in magnetic circuits we have reluctance to oppose setting up of flux in the magnetic circuits. So reluctance may be defined as it is opposition to setting up of flux in the magnetic circuit. It is denoted by capital letter S. Its unit is ampere turn per Weber. Like we calculate resistance as V by I, we can calculate reluctance S as mmf by flux, that is N into I by phi. Unit of N into I is ampere turn and unit of flux is Weber. Therefore, unit of S will be ampere turn per Weber. Ampere turn may be written in short as AT. So AT per WB. WB means Weber. Next definition is permeance. It is reciprocal of reluctance. Its unit is Weber per ampere turn. Next definition is of magnetic field strength H. It is defined as magnetomotive force per unit length. It is denoted by H and its unit is ampere turn per meter. So H is equal to Ni by L, where L is mean length of magnetic circuit. Permeability. It is the ability of material to undergo magnetization when magnetization force is applied. It is denoted by mu. Its unit is Weber per ampere turn into meter. Next we will write the definition of reluctivity. It is reciprocal of permeability. That is reluctivity is 1 by mu. Unit will be ampere turn into meter per Weber. Lastly, we will write the relationship between magnetic flux density and magnetic field strength. That is B equal to mu H. You can write it as B equal to mu R into mu naught into H, where mu R is relative permeability and mu naught is absolute permeability. Remember, mu R is equal to 1 for air medium and mu naught has constant value equal to 4 pi into 10 raised to minus 7. Also now we can write reluctance S equal to L upon mu A. As we write resistance in electric circuit R as rho L upon A. Here L is the mean length of magnetic circuit. Mu is permeability, which we have already studied, and A is the cross-sectional area of magnetic circuit. Dear students, I will stop the class here and continue in next class. Thank you.